Her advisor at the time was a friend of ICTP-SAIFR, Raul Abramo. She's a cosmologist, and as far as I understand, she works on how to use the huge amount of data that are coming out to learn more about the universe, right? So the title of the talk is Pulsar Timing Arrays, a new window into the gravitational wave sky. The floor is yours.
Great, thank you. Yeah, really happy to be here. So I'll be talking about pulsar timing arrays as a new way to measure low-frequency gravitational waves. And so one of the most important measurements of the last decade was the first direct detection of gravitational waves by ground-based interferometers like LIGO. And this measurement is shown over here on the right of the merger of two black holes. And the data from Hanford and Livingston are overplotted over here as measured by LIGO. The first indirect measurement of gravitational waves came from the orbital decay of binaries. And that's shown on this plot on the left over here, where the orbital evolution of these two, of this pulsar that was part of a binary was tracked over a very long amount of time. And you can see the decay of the orbit as agreeing very well with what was predicted by general relativity, so in this curve over here, versus no effect. So this was the first indirect detection that came several decades prior, whereas in a direct observation, you essentially, I'm seeing now how the colors change in this projection. But you can see essentially directly the effect of gravitational waves propagating and changing the light travel time between the arms of these two perpendicular detectors. And roughly what you're measuring is this relative change in length of the arm. So you're seeing the lasers being split and reflecting and recombining over here, and you see an interference pattern showing up, which tells you that you've measured your gravitational waves. And what we're currently seeing is this opening up of a gravitational wave spectrum, so over multiple frequencies, where LIGO is sitting here at this highest frequency end in this plot. So this is the characteristic strain on the y-axis, so the overall amplitude of the gravitational waves that you detect, and the frequency is shown on the x-axis. So the highest frequencies are over here, which you get with these ground-based interferometers. At slightly lower frequencies, there's this planned space mission, LISA. But the topic of this talk are pulsar timing arrays, which are the lowest frequency end of this spectrum. So this is what I'll be focusing on. And this was essentially the second, it's the second frequency range at which we expect to see gravitational waves directly. So these measurements rely on observations of pulsars. Pulsars are these spinning neutron stars that rotate with very stable periods. And every time this period crosses your line of sight, you see a blip over here as shown in this GIF. So this jet crosses the sky, and when it faces the observer sees this blip in a pulse. And these objects are measured with a very, very large degree of precision. And you can think of them as basically very stable clocks. So I'm showing in this table over here just a measurement of one particular pulsar that people make. And this table is showing basically the parameters that are measured in this particular object. And this is just to show the kind of incredible precision that is achieved in measurements of these types of stars. So for example, here you can see the spin frequency measured with all of these decimal places. This pulsar is part of a binary, and the orbital period is known to this huge degree of precision. And each of these numbers are actually measured, right? This isn't a mistake by someone who doesn't know how significant figures work. This is actually measured very, very precisely. So just another example of how precise these are. This is paper from.
Sorry, over how many years was this measurement made?
This is the longest timed pulsar, for example, in nanograv, and this is around 15 years.
And nothing has changed in the 15 years? Or do the numbers change a bit from one year to another?
They do not change very
Okay.
much. Yeah. Yeah.
So I imagine the precision here comes from the fact that we've counted how many periods have happened over 12 years. But so this would be the measurement precision on the average period, but what is the variance in individual periods?
Yeah, so the variance is this weighted root mean square
Okay.
of the timing residual. So it's this microsecond.
Okay, thank you.
Well, fraction. Yeah, cool. So yeah, these are millisecond pulsars that are used for these measurements. So yeah, this is just another example to showcase this. So this is a paper from the Annual Frequency Symposium in 1987, and this paper is called Millisecond Pulsars Rivals Best Atomic Clock Stability. This paper is slightly more recent, I think from 2007, but they're looking at pulsars as a way to, they're using X-ray emission from pulsars as a way to do space navigation. So this is comparing, just again, the stability of the pulsars over several timescales and comparing a few different pulsars with atomic clocks. And at very large timescales, pulsars become quite competitive. Atomic clocks have become better over time, but this is just showing that over long timescales, pulsars do pretty well. So with these very precise clocks, one thing you can do is to try to use them to measure gravitational waves. And the idea is to use each of these stars that we observe in the galaxy as essentially different arms of a gravitational wave detector, similar as you would with an interferometer. And here you're measuring the arrival time of the pulses, so that's the data that you're collecting. And just an order of magnitude here is that the strain amplitude that you can detect is roughly the delay that you observe in the pulses divided by the total observing time. So you're observing these pulses as a gravitational wave passes through. This perturbs the path of these photons, and you see a change in the arrival time of your pulses. So for example, for a target sensitivity, and this is something that is roughly reasonable for some astrophysical sources that you might expect to detect, this would be of order of 10 to the minus 15. If you observe your pulsars for around 10 years, you need to be able to tell that your pulses arrived late or early by around 100 nanoseconds, which is comparable to the stability of the pulsars that we were seeing before. And so this is why now we're able to do this. We're able to measure these delay times relative to some predicted value to the required precision. Okay, so to be a little bit more precise, we can define this redshift, which is the relative change in the pulsar period over time. And you can show that this is proportional to the metric perturbation on Earth. So here, if I have the Earth over here, the pulsar is in some direction
probably a very naive curiosity, because if I understand correctly, you are, let's say, you see that, let's say, the pulsar is changing a little bit its period, and you say, okay, this change is due to a gravitational wave that is passing. But that means that you know the pulsar so well that you exclude any other cause of this delay.
Yeah, so we'll get to the particular characteristics of this. You're not looking at necessarily at an individual pulsar, but rather the correlation between different pulsars, right? So the only thing that's changing that is common across all of these pulsars and that has a particular shape, and we'll see what that shape is, are gravitational waves, but there are many other sources of noise that you need to take into account when you do these
And you know these sources so well that you can, let's say, you can discriminate between.
Well, the point is that you're looking for a very particular signature in the correlation of your pulses.
Okay.
But we'll get to that.
Okay.
But there are definitely a lot of sources of noise that need to be taken into account, but none that look like the signal. Okay. So In this case, I'm showing here a pulsar in a direction p hat, a gravitational wave in a direction omega hat, and this shift in the observed period of the pulsar that you see is proportional to the difference in the metric perturbation between us. So here at the origin, 0 is the Earth, and at the pulsar over here, and then projected along this Earth pulsar axis. So you get this geometric factor in front. And in the case of a gravitational wave in the transverse traceless gauge propagating in the direction of the screen, you can write this in this familiar form. And these are just essentially a plane wave. And the GIF that we were seeing before was essentially when we were seeing this projection. So just to give a sense for what this looks like, this map over here is showing the redshift that you observe in a given pulsar as a function of the location of the pulsar. So each pixel here in the map is what you would see if you had a pulsar located at that position in the sky. And I've placed a source just in this point over here. And what you see is this sort of quadrupolar pattern of the timing, this relative timing residual between when you expected the pulse to arrive and when it actually arrived. The actual values here are not very important. I've normalized this map, but basically everywhere that is red, you'd be seeing pulses that arrive delayed, and everywhere that is blue, you'd be seeing pulses that arrive early. And the source location is where these things meet over here. And so this is just for one source located over there. And you can imagine describing the amplitude of the source as a function of the say parameters that characterize some, let's say, one astrophysical source emission. Sorry?
Yeah, I was going to ask, is there a dependence on, let's say, where this, because this is like a 2D projection, where the source is relative to the pulsars in distance, let's say? Does that affect this map?
Oh, yeah. So the source is going to be located, it's coming from very far away. The pulsars are just in the galaxy. So you're in this regime where, yeah, the legs of your detector are much shorter than the distance to your faraway source. Yeah. OK, so you can imagine describing this just in terms of the parameters of your sources. You can try to search for this in your data, essentially. But what I'm going to show next is what happens when you add more and more sources, right? So I'm going to show a GIF where in each frame I add another source. And these will all contribute equally, so they will all be of equal brightness. And this is basically going to show the central limit theorem in action. So here at the end, I've added a total of 1,000 sources that are equal brightness. And essentially what you see is that you go from this map that is very, let's say, coherent to a map that looks like a Gaussian random field. And this is essentially the stochastic limit of gravitational waves, where instead of describing each source individually by a set number of parameters, you're instead thinking of this map as a statistical field. And the questions that you can answer relate to the moments of the distribution that describes the statistical field. And you've added a bunch of plane waves. So the mean of this field is 0, but you have a non-zero variance that is shown in this curve over here. So this is the angular correlation between timing residuals these redshifts at different times and at different locations. So here A and B denote different locations on this map. And I'm calculating the angular correlation between these. And what you find is this curve over here that's called the Hellings and Downs curve. And so essentially, the signature of these gravitational waves is to produce an angular correlation between how early or delayed your pulses arrive that has this very particular shape. And this is considered, evidence for gravitational waves in your timing residuals. So here, the angular dependence is this C theta AB, which is this approximately quadrupolar shape. So here, as your pulsars are close together, you typically see them arriving either early or delayed in a positively correlated way. As these move further away, they become anti-correlated and eventually correlated again. That's what this curve is showing. So this angular pattern is evidence for gravitational waves. The energy spectrum that you observe, so the amplitude of this variance will depend on the energy spectrum. And this is basically proportional to the total energy density in gravitational waves or the characteristic strain. And this is essentially telling you something about the properties of your sources and what produced this angular pattern. Okay, so this is what was observed pretty recently. About 2 years ago, multiple pulsar timing array collaborations announced some initial evidence for this quadrupolar pattern. This is just an example from the nanograv papers. And this is, again, the spectrum and the angular correlation that was observed in this data set. So for the rest of the talk, I'll mostly discuss this energy spectrum that was measured and what we can sort of learn from these initial measurements. Yeah, this is the same curve as this. Yeah.
And this curve somehow answered the question that I was asking, right? Because it's very specific for the gravitational waves and not other sources of, am I right?
Other sources of noise will not produce this particular shape of angular correlation. Yeah. So this is just how these measurements are made, essentially, the experimental landscape of the field. These measurements depend on radio observation of pulsars. So all of these are radio telescopes around the world. And you have several of these collaborations. So here, nanograv. A new addition in these types of observations is TRIME, the European PTA, and the Australian one over here, Parkes PTA. The sort of new, more recent telescopes are shown here. FAST in China and Meerkat in South Africa are two of the more recent collaborations to announce sort of tentative evidence for these results as well. And for the three first ones that I mentioned, this is just showing the number of pulsars that are observed by each collaboration and how many are unique to them, how many are shared. And you can see that all options in this Venn diagram are populated. But this is just to give a sense of how many pulsars are used for these measurements and how overlapping or not they are. So this initial measurement was made, and I think an interesting question to ask is, what produced them, and what can we learn about the sources from this? So this is again coming back to this characteristic strain as a function of frequency, and in general, the frequency is inversely proportional to the mass of some inspiraling binary. So if LIGO here is measuring, stellar mass black holes, as you go to lower frequencies, the masses are larger, and you're seeing these supermassive black holes that are the most massive black holes in the universe. So a lot of the work that I'll mention today is focused on modeling these known astrophysical, essentially the only relevant astrophysical sources for pulsar timing arrays, and comparing that with these recent observations and trying to understand what we're learning about these sources. So in general, it's an interesting time to be thinking about black holes, in large part motivated by these observations that are popping up. But there are a lot of other things that we already know about supermassive black holes. For the closest black holes, there are very detailed studies of them. So this is showing, for example, the supermassive black hole in our galactic center, and some of, also the galactic center black hole, and nearby sources from these detailed EHT images. And this panel over here is just showing basically where in the universe we observe them. And I'll show a few different options here. But there's this remarkable fact, which is that pretty much every galaxy that we see has one of these very massive black holes at their center. And these are, millions to billion times the mass of the sun, which are these supermassive black holes. So slightly beyond the very nearest black holes that we can supermassive black holes that we see, there are supermassive black holes whose presence is inferred dynamically, but not from the orbit of individual stars, but from kind of bulk motion of stars and gas around them. This is achieved at distances, let's say, less than 100 megaparsecs. And these have been studied essentially when the Hubble Space Telescope launched, is when most of this work was done. So the mass of these black holes can be inferred dynamically, and people found a lot of correlations between properties of the host galaxies and the masses of the black holes that suggested that these black holes and the galaxies grew together in some way. Beyond our local universe, we're limited to seeing supermassive black holes that are in the process of accreting. So we observe these very bright quasars, which are thought to be powered by matter that is essentially falling into the central supermassive black hole and radiating as they do that. So kind of a simple way to think about what black holes can tell us, or about what quasar observations can tell us about supermassive black holes, comes basically from a statement of energy conservation, where you can imagine some total amount of matter that is falling into the black hole. It radiates some fraction epsilon r here. And so if you observe the number of quasars per total luminosity, you can infer essentially the total mass that has been accumulated into black holes over cosmic history. And these are observed you can observe these very distant sources. And in particular, JWST is sort of pushing the redshift boundary of where we observe these types of sources. And I think they're very interesting prospects in understanding the evolution of supermassive black holes over cosmic history from this. From pulsar timing arrays, what we think we're observing are supermassive black holes in the process of merger, right? So I mentioned that every galaxy seems to have a black hole, a supermassive black hole at its center. Galaxies are known to merge, so the central supermassive black hole is expected to merge, or may merge as well. And if they do, and they can shrink to these very small separations, then you'd expect to see them in the PTA band in this very early in spiral stage. So in an experiment like LIGO, for example, you would see these objects as they are actually merging. In PTAs, you're catching them a little bit earlier in this very slow stage of their in spiral. And the particular redshift at which these are produced is not known, for sure. It's not something that you can just directly infer. But just from kind of hierarchical structure formation argument, you expect these to come from the pretty late universe. So these are will typically be at this end stage where your black holes have grown. Okay, so one thing I've been pretty interested in is in joining these things. We know that these black holes have grown by accretion because we observe quasars. We know that they have changed and grown from merger. And one thing that I looked at recently was how do you combine these things to learn about the history of the evolution of these sources. But what I'll focus on now is on the gravitational wave emission itself. So how do we understand the emission of these low-frequency gravitational waves that we think we're seeing in pulsar timing arrays, and how do we relate this to think about properties of these supermassive black holes? So the basic way to think about this is that, again, this overall correlation between the timing residuals is proportional to the overall energy density in gravitational waves. So the overall energy density is written over here, and it's basically just given by the energy spectrum produced by these merging binaries integrated over all of the sources that produce them, right? So this is just the energy spectrum per source integrated over all possible sources. And this energy spectrum is basically determined by, so we think that we're observing these sources in this early in spiral where their emission is dominated, where their evolution is dominated by gravitational radiation. And this allows you to predict what this energy spectrum is entirely. You're just equating the change in the orbital energy with the power radiated in gravitational waves. And this allows you to predict what this energy spectrum actually should be. Is there, yeah. Sure, yeah.
In this forum, where do you fold in the information about the distribution of the distances of these black holes, no? They would be at generic distance.
Yeah, so they all evolve in the same way, right? All of the sources are evolving through frequency in the same way. So you can write this as, I mean, there's some change in the orbit per unit time, but they also spend a certain amount of time per frequency. And so you don't need to specifically describe how the way that the orbital separation changes is just determined by how much energy it's losing.
So basically, okay, I guess you are saying that if you fix the mass, I mean, then eventually you integrate over the mass, but for any mass, the frequency determines everything.
Yeah.
For any mass, you look at one frequency. So you're assuming they're emitting at that frequency. Okay.
Yeah. Okay. Right, so because the orbital evolution of these sources is determined by gravitational wave emission, you can predict this energy spectrum precisely. And this is why there's a strong prediction for what the power law of this energy spectrum should look like. And so if you want to predict what you should observe in these pulsar timing array experiments, basically the main thing you need to worry about is this overall amplitude, which is dictated by the number of merging sources. And so what I talked about in my seminar on Monday, and I'll quickly go over here, is that there's actually a very simple way to predict what the amplitude of this background should be. And it's basically just a function of the abundance of black holes today at redshift 0. So there's a very simple way to relate observations that we can make of the universe today with what the amplitude of this gravitational wave background should be, such that we can compare, some prediction based on one set of observations with a direct measurement from gravitational waves. And second, I'll talk about how we can model these spectral fluctuations and get a bit more information about the typical number of sources that are contributing to this gravitational wave background. But so at the moment, from these sets of observations, you're basically measuring these two things: an overall amplitude that depends primarily on the number of black holes, and the effect from statistical fluctuations on the number of sources that is basically telling you something about the typical number of sources contributing to the gravitational wave background. Okay. So the general idea here is that we need to be able to predict what this binary merger rate density should be, so the number of sources merging as a function of a set of parameters that describes this emission. So here the redshift and the mass, for instance. And the key insight is that you can relate the number of sources today with the number of merging binaries, because essentially whatever happened in the evolution of these sources needs to result in the population of black holes that we see today, right? So if I see the abundance of black holes of a given mass today, then, for example, if I say that all black holes merged exactly once in the history of the universe, then I can just equate the number of single black holes today with the number of binaries that merged at some point in the past. So I can basically just equate these two things. And if I assume that there have been more mergers in the past, this essentially doesn't change the picture very much because you're making your black holes smaller and smaller, and so they contribute less and less to the gravitational wave signal. So essentially, this number of black holes at redshift 0 determines everything about the emission of gravitational waves that you would see. And what's interesting about making this connection is that you can rewrite your characteristic strain, so the total emission in gravitational waves, to the single black hole mass function that we see today. And what this means is that there's basically nowhere to hide. So this quantity is directly observable, that we can make from electromagnetic observations. If I wanted to take, for example, an upper limit of the total gravitational wave background that I should see, I can just write this as an average over the redshift, over the mass ratio, and these are maximized by taking the redshift to 0, taking the mass ratio to 1/4. And so there's a generic upper limit that one can predict for the gravitational wave background just based on observations of the single black hole mass function today. And we can measure this directly. So for example, from these observations of the scaling relations that I mentioned before, so the relation between some galaxy property and the black hole mass, of the number of galaxies per this property, I can predict what this black hole mass function should be. And I could plug this in here, and I can predict what the gravitational wave background what should be the maximum gravitational wave background that I could possibly observe, okay? And what we showed in this work is that when we do this, so we take several measurements of the of the black hole mass function, and I plug that into that expression, I find these points over here, right? So each measurement here of the mass density of black holes today corresponds to a point over here in this bottom part of this plot. And these points over here are measurements by the Pulsar Timing Array collaboration. So each of these is one of those collaborations that I mentioned earlier. And we found it curious that even though this is an upper limit prediction, the actual measurement that was made was a little bit higher than that. So the observed gravitational waves seem to be a little bit louder than what you would predict the maximum amplitude to be, which is what we pointed out in this work. So we also explored a little bit what could be going wrong in this prediction. And so I mentioned before that quasar observations give us a handle on this total mass density in black holes. And the kernel is shown in this red plot over here, whereas gravitational waves, the signal is basically proportional to mass to the 5/3, which is shown in this blue kernel over here. And so the gravitational wave signal is basically dominated by the most massive sources that you have. And if you want to change your predictions without messing this picture too much, you basically find that you need to boost the abundance of these most massive black holes relative to what you would have predicted. So essentially, if you want to, let's say, fix this problem, you would require about 4 to 10 larger abundance of black holes than what we currently measure. Or if you were to increase the typical masses that contribute to this gravitational wave background, you would be required to populate this plot in a region where we have not observed before. So this is showing the mass of the black hole in the y-axis and a galaxy property that we use to predict that is a property of the galaxy that is related, that it correlates with the mass of the black hole. And these points are where we have observed objects to lie, and you would require objects to live over here where we have never seen them in order for you to match these observations. Okay? Yep.
So just a quick question. Could it be possible that this, for example, this difference in the gravitational wave density that you need could be coming from different sources of gravitational waves instead of just supermassive black holes, such as cosmological, or that fill up that excess that you need?
Yeah, so the only option of known physics are supermassive black holes. And so this would be the entire prediction. I mean, these are, early measurements. There is room for the measurements to be wrong. But I think this comparison can illuminate if there is a source that we're not accounting for or not. Yeah. Okay. So essentially, you're led to this conclusion that either you need a larger abundance of black holes, or you need to change the typical contribution, the typical mass that contributes to your gravitational wave signal. I'm going to talk about something a little bit different, which is taking this prediction maybe a step further, where we've been talking about the overall amplitude of the gravitational wave background, but we do measure a gravitational wave spectrum over here. So this is a measurement in each frequency. And the amplitude of the gravitational wave background that we've been computing is basically this cosmic average of the number of sources. But in a given realization of the universe, you'll have fluctuations in the number of sources, right? So you'll typically you might not live exactly in the cosmic average, but with a fluctuation in this number of sources. And these effects from finite and discrete number of sources will lead to fluctuations in the spectrum that you can model and learn something about this population from that. So the mean, for example, is shown over here of this prediction in dashed, and in the presence of these fluctuations, the median falls off, and you also have these frequency to frequency fluctuations. So there are basically two effects that tell you that will give you more information. One of them is this frequency to frequency fluctuation, and the other is the drop off of this median. And the basic approach to model this is to just describe the emission in each frequency bin as the sum of the emission from each individual sources. And where each of the individual sources is basically drawn from a luminosity function, so a number of sources per total brightness. And this quantity basically tells you, it's basically the fundamental quantity that you need to model all of your signatures in these gravitational wave observations. So for example, the mean number of sources is just the integral over this. The mean gravitational wave background is this first moment. The spatial fluctuations are the second moment, which we also worked out in this paper over here. And examples of these luminosity functions, quote unquote, for gravitational waves are shown in this panel. And just like the gravitational wave background, most of the contribution came from a characteristic mass. Most of the contribution here can be attributed to a peak gravitational wave amplitude. So if I plot the kernel again here, this is peaked in much a similar way as the mass kernel was peaked for the gravitational wave strain. So a useful quantity to define here is this characteristic number of sources, which is the total, the integral over this curve, divided by this peak. So if all of my contribution came from just this most important peak strain, how many sources would I need? And this number controls the importance of this effect, right? When this number is of order 1, then these Poisson fluctuations become important, and these signatures that I just described here become relevant. And you can show that this scales very strongly with this peak mass that I had defined before, and with the frequency that you observe. So it's a very strongly falling function of frequency. Essentially, this is why at some point in your PTA spectrum, you expect to see this to become important, because this is a very strongly falling function, and it crosses 1 at within the spectrum that you observe. So we showed in this work that you can just compute this probability distribution of your strain, exactly. So the state of the art was to just Monte Carlo these distributions, but we showed that you can compute it exactly, and in particular, that it can be just described in terms of only 2 parameters, 2 effective parameters that capture all of the important information in your data. So this mean strain and this characteristic number of sources fully describe what you can see in your spectrum. So you only need these 2 parameters, and you can compute these distributions and compare that with your data and do inference on these 2 parameters. So this is what we did. This is comparing the approach that we took with the result from Nanograv. So this is from one of the Pulsar Timing Array collaborations that I had mentioned. And essentially here, this is showing the approach that they take, basically simulating all of these libraries of supermassive black hole to essentially produce similar luminosity functions that I had described for supermassive black holes. They sample these distributions, but then because there are a lot of free parameters that you need, and you need to have a distribution for each of them, these are interpolated using Gaussian processes, and only then are they compared with the data. And what we showed is that because we were able to summarize this into these 2 effective parameters that actually describe your data, this becomes really fast. So you can just specify these 2 parameters, compute these distributions analytically, compare it with the spectrum. And you can just do this on a grid, basically, because it's just 2 parameters, and then infer them from the data, and then maybe convert them to relevant physical parameters that you care about astrophysically. So this is what we did in this paper over here. And so we reanalyzed this spectrum from pulsar timing arrays, taking this full distribution into account. So this is shown in this contour, in this blue contour over here, what you get by fitting the pulsar timing array results from Nanograv. The x-axis is showing this peak mass, so the mass that most contributes to the gravitational wave background. So here I've converted these 2 effective parameters back into these physical parameters, the mass density in black holes and this peak mass that contributes to the background. And you can think of this as just an overall normalization in your number of black holes, and this is just the peak contribution in terms of mass. So this blue contour is what we find from our fit. This red is what you get from these local observations of the present mass density that you would expect. This gap between these 2 contours is this discrepancy that I had mentioned before in terms of the amplitude of your prediction and your observation. And what we basically show is that you do not find evidence for these Poisson fluctuations, which allow you to place a limit on the typical number of sources contributing. So this upper left corner over here is where you recover this Gaussian limit of many sources, of many faint sources. And the scenario that I had mentioned before, where you just increase the typical mass of the black hole that contributes to the background, would lie basically over here in this bottom right corner, which we kind of rule out with this measurement. So you really require a larger number of fainter black holes for this to fit together. So the dashed lines here show lines of constant characteristic strain. If you had only measured the amplitude of the gravitational wave background, your measurement would be completely degenerate along this line. But the fact that it's squished along this upper left corner results from this measurement of this typical number of sources from the non-observation of these Poisson fluctuations. So in summary, there's already some information about the typical number of sources in PTA observations, which we were able to fish out with this clearer modeling of the sources. Yeah, the dotted lines are lines of constant characteristic number of sources. Yeah. Yeah. Yes, you can never, there's always a Gaussian limit where you can't tell it apart, right? So there's always an infinite volume to this side. Yeah. Okay. So this is essentially what current data is able to tell us. And I'll just comment on, how can we improve? So in terms of the measurements that are, in terms of the measurements that we make of pulsar timing arrays, basically the minimum frequency that you observe is proportional to the inverse of the observing time. And you can just observe things for longer and observe lower frequencies. The signal to noise goes as the square root of the total observing time. It's linear with the number of pulsars. And this is the noise spectrum of your pulsars. So basically, it may seem a little daunting to see these, 15, 20-year time series that are used for these measurements. But a way that a lot of these collaborations are improving is actually by improving the denominator over here. So building more precise telescopes where the error on the arrival time of your pulses is lower, and you improve your sensitivity through improvements in the telescope. And this is already seen with Meerkat, for example, and with the Chinese PTA. And you also have these newer telescopes in the horizon. So SKA and DSA 2000 are two upcoming telescopes that will be added to this. And so this is basically shown in this plot over here. So if you continue observing all of the pulsars in nanograv, you get the sensitivity curve shown in this solid curve over here. The gray violin plots are current measurements by nanograv. And then, for example, this dashed curve over here is showing the sensitivity of this DSA 2000, which improves this higher frequency regime. And in these higher frequencies is where you have this higher probability of seeing one source that is brighter than all of the other ones, again, because of this Poisson effect. And the idea, so this plot over here is showing the model distribution of, so these are the distributions that I was showing before. And the solid histogram, essentially, the steps over here, are one realization of this gravitational wave background. So this is just showing an example where a brighter source was sampled at this frequency, and you can hope to detect these individual brighter sources if they are substantially above the background. So this is, an analogy between this current state of the measurement and, for example, the CMB. Currently, the measurement that we have is essentially a monopole, and you have some tentative measurements of the spectrum. And the idea is to resolve this background and detect, the location of individual sources, and to resolve this background, basically. So I'll leave you with my conclusions. Pulsar timing arrays open this window into the gravitational wave sky, and I think an interesting question to ask is, what produced them? There's a well-defined prediction for supermassive black holes in terms of a small number of few parameters and a small number of free parameters, and that can be directly compared with existing electromagnetic observations that allows us to test our hypotheses about what did or didn't produce these gravitational waves. I also mentioned that there's already more information from spectral fluctuations, and in general that the self-consistent modeling between the gravitational wave signatures and electromagnetic observations will teach us more about these sources. Thanks.
Thank you very much. Time for question. Maybe we can start from the Zoom.
Yeah, I had a very naive question, which I think I know the answer to, but just to make sure. So when you put the sources for the gravitational waves, it has to be black holes. It can't be like dark matter subhalos or anything like that because they're too big. Is that right?
Yeah.
They wouldn't produce the. Okay.
Yeah.
Okay. Sorry, and I also meant to say very nice talk. Sorry.
Okay, I'm going to ask a very naive question, which is perhaps just wrong. I'm not an expert in this. In the case of the CMB, that has huge implications for cosmology. Is there an analog for this?
Yeah, I guess this is the disclaimer, is an analogy between the state of the measurements and not necessarily of the information content. So here, the idea is to build a model for what the standard prediction from supermassive black holes would be, right? So we have a hypothesis that the gravitational wave background is produced by astrophysical sources. And what this is doing is outlining what black holes can or can't do in terms of your gravitational wave prediction. This is, building the standard model for what they would do.
But this is not, in the CMB, one imagines that this is a relic of the Big Bang, and I don't see, you're not using that terminology here. You're looking more maybe for recent things, which are these supermassive black holes.
Yeah, again, this is an analogy for where the measurement is. So, just to say, we've measured a monopole. It's just an unresolved background. This isn't to say that we're going to measure, the same physics. It's just, what we think we're measuring is our merging black holes that were at the center of galaxies. Yeah.
So the CMB in principle relates to things that happened way before galaxies were formed.
Yes.
Yes, so there should be an analog, there should be a relic, if you wish, of gravitational radiation coming from the Big Bang, okay?
Yes, so if you can think of the galaxies maybe as a foreground, for example, if you're interested in, gravitational waves of a primordial origin. And so there is another whole class of predictions from, cosmological sources and for, sources of primordial sources, essentially.
At the moment you're looking at things by using the galaxy itself as a telescope, in a sense. Things which are of characteristic distances between these pulsars are of galactic size. Do you need to go and compare things between us and Andromeda to actually look at things that happened earlier?
No. So you're using, sorry, what do you mean? So you're using pulsars in the galaxy just to measure, you're just measuring the arrival time of your pulses, but the frequency of the gravitational wave that you observe is just proportional to inverse of the observing time. And if you have a cosmological source that produces gravitational waves in those frequencies, then you would see them with this telescope as well. And there are predictions of cosmological sources in these frequencies.
Okay, that's what I wanted to know.
Oh,
Thank you.
okay, got it.
Okay, perhaps we can pass here in the room. So we have a question there.
Hi, thanks for the talk. Mine's a very quick question. In slide 34, when you spoke about the outlook, sorry, I think I got distracted. What's the P_n in the signal noise ratio?
So this is just the noise spectrum of the arrival time of pulses, basically.
Okay, so simply that means make the telescopes better such that the noise is, okay.
Yeah, so this is just improving the telescope such that you have a better measurement of the arrival time of the pulse. And yeah, decrease.
More question? Yeah.
Can you go back to your conclusions? And the third conclusion, can you expand a little bit what you mean by self-consistent modeling between electromagnetic and supermassive black hole sources?
Yeah, so this is, for example, this prediction of the amplitude of the gravitational wave background based on our existing measurements of the abundance of black holes today. This is a required consistency, right? If the sources that you observed in pulsar timing arrays are merging supermassive black holes, then it must be true then that your amplitude is lower than this upper limit that I predicted, that we predicted, right? So this is an example of a consistency that is required, and that's whether or not this is satisfied is already telling us something about, it can tell us something about the nature of your sources.
It's not that you have electromagnetic counterparts of supermassive.
Not right now, but it's definitely a direction, an interesting direction.
So when I understood, your work showed this discrepancy between the scaling model for the population of black holes and the measured data, but I didn't understand. Do you have any ideas for what leads to this discrepancy? Is the scaling model incorrect? Is there something wrong with the assumptions you were telling us lead to this population in the current day, or is there something very strange wrong with the data or something like this?
I think that, the only way for this to fail and for you to have your sources being supermassive black holes is that there's something wrong with the measurements, either from the mass function side and the scaling relations or from the pulsar timing array side. There's not really another option. So there must be an issue in the measurements if the sources are only supermassive black holes. And we've been looking at what could be happening, right? So what isn't being taken into account, for example. And I think, again, that there are possible things that can go wrong in both of these measurements. From the pulsar timing array side, it's a new measurement, and there are, so for example, some things depend on how you model the noise in pulsars. And there are, things like this that one could look at. I in particular have looked at measurements from the mass function and potential systematics that can go on there, but there isn't a clear answer at the moment of, this is the thing that we did wrong, and this is why the predictions are inconsistent. I think that's still something I'm interested in understanding.
Okay, thanks.
More?
Okay. Then I have a curiosity.
Also Orazio over there.
Sorry.
Yeah, also curiosity about the data. So you showed a lot of sites in the world, US, Australia, South Africa. Do they actually correlate in any of the experiments, the different sites, or is it just array at the individual site?
So each telescope, each PTA is composed of different telescopes But the telescopes, so there are joint analyses that combine these, but each of the PTA uses data from the specific set of telescopes that are separate from each other.
So what the scaling of the maximum L you can appreciate with different pulsars.
Yeah.
Why L scales with the square root of the number of?
Yeah, that's just counting number of measurements versus number of variables that you want to infer. So the total number so if you measure n pulsars and you want to infer, so the number of
12 plus 1 for each L.
Yeah, it's L plus 1 squared. And so it's, the number of
Yeah, but also
modes.
the measurements are actually n squared, no? Because it's the number of pairs. I thought it was both should be squared, but no, you're telling me.
No, so the number of measurements is just the number of pulsars.
Okay, independent measurement, yes.
Yeah.
Okay.
Do we have any more questions? Okay, if not, we can thank our speaker again.